Hi, I'm going to talk about new frontiers in artificial intelligence. Let me start by giving the dictionary definition of artificial intelligence. Artificial intelligence is the simulation of human intelligence processes by machines. Let me give you several examples. Throughout my talk, this half-brain, half-electric circuit illustration is going to represent an algorithm in a computer. So in this case, the algorithm takes in as input an image and has to produce an output, which is the label indicating what's inside the image. In this case, it's an image of the dog, so the algorithm would predict a dog. This type of algorithm is called image recognition algorithms, and in recent years have become really successful in doing image recognition tasks. We can even see these algorithms deployed in certain commercial softwares like Google Photos. Here I'm showing you an example from my personal image collection where I just took few images and labeled them with my middle son, Uri, and then when I search for Uri in the search bar, I get all the images in the dataset which contains Uri inside them. And some of these examples, for example, the image here on the right, is pretty non-trivial because you see his face is kind of a little bit blocked and it's hard to see. In fact, the algorithm is even succeeding in cases where Uri has a really different appearance. In this case, he was dressed up like what he considers to be a scary clown. He colored his hair and put some makeup on, but still the algorithm is not confused and recognized correctly that this is Uri. So these type of algorithms are working really well now, comparable to human recognition system. And there are even examples where algorithms, AI algorithms that exist today perform even better, or what we say superhuman abilities. For example, in this case, the task is you're given a black and white image, and the task is to add color to the image. And I guess you all agree with me that this type of task is something that most of us cannot really accomplish very well. We can, when we see a colored image, kind of say if it's colored well or not, but it's hard for us to come up with good colors and color an image. Another thing to note about this task is that it requires some sort of artificial intelligence in the sense that in order to color, for example, a face of a boy, you have to understand that this is a boy and put the right color. So this is a really interesting task. And another very kind of popular and important task that uses image recognition is in the field of autonomous driving. So in autonomous driving, there are cameras on the car taking images of the road. And one of the tasks of the algorithm is to recognize different cars on the road and also signs and markings on the roads. And the last kind of field which is becoming really popular in the last several years is using those type of algorithms for medical imaging. The premise is basically facilitate the work of radiologists, increasing their bandwidth, lowering their error rates, and even help them train. In my lab, in the Weizmann Institute, we try to generalize or take this algorithm to the next step. If so far I showed you applications of algorithms that process two-dimensional images, which are like grid of pixels, what we try to do is generalize these algorithms to work with a more general data, what we call irregular data. Irregular data is like an umbrella name for several types of data. It can include three-dimensional shapes, like shown on the top left, or point clouds measured by lidars, or even more abstract data structures like graphs. Graphs can model interaction between people, networks, or even molecules. So this type of data is abundant. There's many different sensors that achieve this data with high quantities, and there is a dire need for algorithms that process them and learn this data. What I'm going to talk about today are two specific projects we've done in the lab that use or take advantage of irregular data. The first is three-dimensional understanding. Three-dimensional understanding is the type of task that humans take or think of very intuitively. And the task is you're given a bunch of two-dimensional images, and you have to understand what is the geometry or the shape that is shown in the images. In this case, you see several images of a skull object sitting on a table, and the goal is to understand exactly the shape of the skull in 3D. This type of task is a classical problem in computer vision that has been researched for many years. However, this new area of artificial intelligence allows us to come up with new approaches to solve it. What we've done in this project is basically we model the process of generating an image from a three-dimensional structure into the algorithm and let him figure the rest. So what is exactly this process? So think about this blue dot here as the camera, and think that you're taking an image of some scene. For example, a scene which includes this owl statue. So how do the color of a pixel in your camera is being prescribed? What you have to do is to think about a ray, shown in red, that's emanating from your camera and intersecting the surface. The amount of light reflected from the surface toward this ray is the color of the pixel. Now, if you think about this is a physical process, but this is the physical process that kind of governs the creation of images. What we've done here is we kind of embedded this physical process into an artificial intelligence algorithm and let the algorithm figure out all the unknowns. What are the unknowns here? The unknowns are where the camera is sitting in space and what is the three-dimensional space. When he actually was fed with two-dimensional images as input. Here is the result of what the algorithm was able to achieve from these two-dimensional sets of images. I'm going to show here a couple of examples. The top one is, again, this skull object, and the bottom is some sort of a statue, a golden statue of a bunny doing yoga. On the left column, these short clips show the three-dimensional structure as the algorithm inferred from the images only. And on the right, the algorithm also, in the process of understanding the scene, he has also to kind of infer what is the material that these objects have. And what you can see here is that the algorithm learned the geometry in a kind of a plausible ways and is able to generate novel views, that is, looking at the objects from directions that were not given to him as input in a very realistic way. And in fact, the algorithm can even achieve more. You can actually ask the algorithm to switch between the materials of these two objects. So you can get some sort of a golden skull and a bone-like statue. The ability to predict things that haven't been given to an algorithm in its training stage is called a generalization. And this is really the important part of artificial intelligence, being able to produce something that wasn't seen before. The second project I wanted to talk to you about is related to ultrasound navigation. So what is ultrasound navigation all about? So the field of ultrasound experienced a major revolution in the past several years, where ultrasound machines as a hardware became very small, affordable, and basically can connect to any personal phone or tablet. Now, when you think about that, you can ask yourself, why then we don't see ultrasound machine everywhere? When I go to my general physician or in ambulances, and the reason really is that using this machine requires a non-trivial amount of expertise. In order to produce an ultrasound image, you really need to know how to operate it, and it takes a lot of time to develop this type of expertise. This project kind of put the goal of kind of bridging this gap using AI software. That is, putting some sort of software on the machine that will allow inexperienced users to use an ultrasound machine successfully. If this barrier of expertise is brought down, then we can kind of envision the ultrasound machine be used in places it hasn't been used before or not as often. For example, in emergency rooms, in ambulances, but even outside the hospital. For example, at schools, nursing homes, or even third world countries. So what is exactly the challenge in operating an ultrasound machine? The challenge is that you have to place the probe, which is this white object shown here, in the correct position on the body, but also with the correct angle with respect to your heart. And only if you place it in that specific exact pose, you're able to achieve an image which can be used for further diagnostic. Okay? And if you're not able to reach to that position, you're basically your image are of no use. So the question is how to produce those images. This project kind of draw inspiration from the very successful navigation software that we all use and know. So what is exactly navigation software? When I get into my car, I want to drive to someplace far, I type in the target address, and the navigation software breaks down this seemingly complicated task of getting very far to small, digestible, primitive tasks that everybody can achieve, everybody that knows how to operate a car. For example, keep straight, turn right, and so on. So this idea of taking a complicated task and breaking it into a small task that every person can do can also be used in other things like medical imaging. So how can we take the task of placing the transducer, the probe of the ultrasound, correctly on the human body and break it down to small parts which everybody, or at least a large part of the population can do. So the idea here was to use the ability of persons to basically match kind of a Simon Says game, where to match or place two crows one on top of the other. What you're going to see here in the movie is this application where you see place the ultrasound image, and on the top left you can see a blue cross. The blue cross is like the transducer, and all the user have to do is to move the blue cross and tilt it or rotate it. Here now he has to tilt it in order to put the two crosses together. So it's a little bit like a game, and once you're able to put the two crosses together, the software tells you stop, you reached your destinations, and now it prepares kind of a clip. In this case, it's the 4-chamber view of the heart. And now this clip can be sent via a cloud to a doctor, a cardiologist, to interpret it, or even fed to another AI algorithm that automatically extracts some quantitative information out of this clip. So again, the idea of this project was to break down a complicated task of ultrasound navigation to something that can be used by novice user, and by that facilitating, allowing these machines to be more widespread. So to sum up, I've showed you two projects, one related to three-dimensional understanding, and the other one to navigation of ultrasound machines. Both these projects are related to irregular data and artificial intelligence, and we hope to keep developing this type of field, we and other labs around the world. Thank you very much.